Good morning to all of you. So today I will discuss the how we can simulate a Verilog code using the IC design. So for Xilinx 14.7. So first you double click on this icon IC design suite 14.7. So the screen will come and you just make OK. And if any existing previous project is open, first you go to the file, then close project. So that will close all the previous project. So now I will start a new project that I want to simulate or synthesis in this IC simulator. So first you go to the name of the project. Suppose I want to design a half adder. Just I am giving the name half adder. So by default the location will store in the C drive. So don't do anything. So do the just next. So a window will come where the different project name and there is some product category family. Here you can see that there are a lot of vertex and Spartan families are there. Okay, so depending on the demands, so which hardware you have, so based on that I will choose my device family. So preferably in my we have choosing the vertex 6. So there is a devices also there. There are a lot of devices are there. So by default what is coming that I don't change. So package, speed, everything is there. And another thing is that preferred language you can do the VHDL and Verilog. So but you can know that the Verilog is far better than the VHDL. So basically commercially you can use this Verilog code. So then you go for next. So then finish. After that you will go to the project window. So in the bar, go to the new source. Then I will write the Verilog module of that particular project. So I have given the name half add. So same name I have to give here. So and you can also click in Verilog module. So that means next, and here a port name is given. So here input I will give the AB, and for a half adder sum is there and the carry. These are all output. So I have to select output. So if these are all single bits, so I don't mention the MSB, LSB, all these things. So if it is a bigger bit, so I have to mention 320 like that. So but it is a single bit, so I will just select input as well as the output and go to the next. So now finish. In the window, it is coming the program. You can see that the module half add, input AB, output SC, and you can see that this is the module is half add that is coming here. So now what you have to do? So just I have to assign sum equal to sum. We know that it is a XOR B, A XOR B, and carry equal to assign C equal to A and B. So these are the different syntax you have to remember. Okay, how to write it. So then you can see that they are in module. So that means this is my Verilog code of the half adder. You can just basically see that assign S will be equal to A XOR B and carry that is equal to A and B. Okay. So after that I have to save it. Save. So then I will check whether my code I will check the syntax of this code. Whatever I am writing, whether it is the technically or whatever, if any errors are not. So it is a very smaller code. So you can see that in this window there is a error is 0, number of warning is 0, number of infos are zeros. So that means my code is right correctly. So no syntax error is there. So after that what I will do, so you can check the technology schematic of that. That means I will synthesize the code. So then the report will come. Okay, automatically half adder its input ports are A, B, and output are. So if you double click, there is a number of things, number of diagrams based on the, you can check it, 2 LEDs, lookup table. Okay, so A, B input, and it is the 2 buffers are there, input and output side there is a buffer, and we will see the technology schematic diagram. Okay, technology schematic diagram. So that you can check, and another RTL, register transfer logic, that you can also see, and you can see that. So you can also check its truth table, everything you can also check. You can check in technology schematic. So if you double click on LET, you can check the LET on whatever it is an AND gate. So its schematic, its equation, truth table, and Carnot map. How you can all these things I can also check from this if you double click on this. And you can also double click on the lower LETs. Lower LET basically XOR gate, to input XOR gate, and its equation, truth table, and Carnot map, everything will be given. So you can also check it for your visual purpose. You can also see. Now if I want to see the report, what report it is coming, so just that report will, a very big report will generate, where basically as a VLSI designer, our aim or a target, we have taken the Vertex 6, this device family, and what are the number of LUTs, slice LUTs, how many required. So that means in our design it is a very small design, so it is required 2 LUTs. And in this device, Vertex 6 device, this particular device has 1,50,720 LUTs are there. Out of this, only my design is taking only 2 LUTs. Okay, so the and number of logic, also number of LUT flip flop, how many, number of unused flip flop. So all these things, information, number of IOB, input output block, number of ISBs, input output block. It has 600 total IOBs are there. Out of this, we are taking 4 only, 2 for input, 2 for other output. That is the information, area information we are getting here. And the combinational path delay, that is 0.970 nanosecond. That is our combinational path delay. That means you are giving the input, and after 0.97 nanosecond you are getting the output of that. And that information, you will delay information, is a pure combinational circuit, so no information about the clock frequency, that is not we are getting here. And computation time, XST completion time 6 nanosecond, and total CPU to compute this program 5.4 nanoseconds. So these are the different information, and total memory uses you can also in terms of kilobyte it is using. So this is the synthesis result we are getting from this synthesis report. Now another very important thing is that how we can check the waveform of that particular hardware. So for that I will go to the new source, then I just give the name test2 with just another name. Hardware I have given here, but for the simulation waveform I will give another name, that is the test2, and I will click on the value of text picture. Now next, then finish. So new window will come, and that is basically, this is for the test bench. Okay, now it is in implementation mode. Now we will simulate, check in simulation modes. Okay, so in the simulation mode, to write the test bench, what I have to do, you just check it. So A, B, 2 are inputs are there. 2 input means total 2 to the power 2 means 4 combinations will be there. So 4 out of these 4 combinations, so I will give 0 0 0 0 0 1, then 1 0 1, 4 combination, as we are using the 2 input. So and 1 1. So this is my the test bench. It is very important to check the functionally whether your design is correct or not. So to check it, we have to write the test bench of that particular. So whenever you are checking it, test2, you have to click in test2, then only the iSim simulator will be activated. Okay, you can check the behavioral check syntax, and after that you have to double click on the simulate behavioral modeling. So if you double click on that, so a new window will come where basically we will check what are the input waveform and their corresponding output waveform will come. Okay, it will take some times because sometimes it will, okay, a new window will come. Okay, now after that you will see that this value A, B, these are the input, sum and carry, these are the output. So but you will see that at the end, whatever the values are given, in the end we are giving 1 1. So that result is showing here 1 1 for input 1 1, sum equal to 0, carry equal to 1. So to visualize all the waveform in a single, so you have to check this zoom in full view. So if you do this, then only whatever the combination you have given, this is A B 0 0, sum 0, carry also 0, sum 0, carry 0. Then for A equal to 0, B equal to 1, then carry equal to 0, sum equal to 1. Also it is also 1 0, sum 1, carry 1. And when both the inputs are 1 1, then only you can see that sum is 0 and carry is equal to 1. So we have taken the 100 nanosecond stop, 100 nanosecond pulse width. So that's why you are giving in the code. You can see that this has delay has 100. Matlab, so it's on and off time we are giving a 100 nanosecond. Okay, so that is clearly mentioning in the waveform also. It is also showing 100 nanosecond. After 100 nanosecond, the transition is changing. Okay, so transition of the waveform. Okay, so that you can say it is the clock period of that. So now pulse width basically. So this is the waveform. So if your code is functionally correct, then we can see my design is correct. So after seeing this, you can also copy this waveform in the pin preview. From that you can also take whatever the waveform you are getting, so that you can take the snapshot from here also. And another thing is that, so that means my design hardware, it is functionally correct. Okay, this is the test bench, and if you go to the implementation mode again, and you can also check its there is a lot of tools are there, that is the under implementation design. So you will see that there is a place and route is also there. So in our design we have find the information of area, delay, and now another thing is that the power consumption, how much power my design is consuming. Yeah, this Xilinx is also provided. X power analyzer is also one of the very not so much sophisticated, but it is there is a power estimation it is providing, but that is a, so if we double click on that X power analyzer, you also see there is another new screen will come. So here we will obtain information of power consumption, but that is not a exact one. So compared to the Cadence or Synopsys tools, okay, but for overall idea we will get some idea of the power consumption. That is not the exact one, okay. So as a most of the VLSI people, for the simulation and their waveform checking and for the Verilog whether the design is correct or not, we first, any VLSI designer, they will first run the Verilog code in the Xilinx, okay. So if you write the Verilog code in proper way, then and it is successfully simulated and synthesized in the Xilinx software, okay. So then the same code we can simulate in very sophisticated ASIC tool like the Synopsys and the Cadence tool. These are the very commercially very costly tools, so you can easily simulate and synthesize in the Cadence and Synopsys tool also. So Xilinx is a very good tool for the beginners or for getting the information of area, delay and power, basic idea. So that is a very good tool for, and it is also sometimes easily available. So that's why Xilinx tools are very important. So you can see that it is taking some time, okay. So that means whatever the now translating, then mapping, place and route, so at least 2 to 3 minutes it will take it, okay. So all the your design, if you see in the Vertex 6 hardware kit, okay. So to yeah, just that code will be downloaded in that particular Vertex, but here basically you are not downloading any the code. So for that you have to connect with proper tag, okay. So proper there are a lot of procedures are there, but for simulation purpose we are showing all these things, okay. But it can be done also, whatever the Verilog code we are writing for the half adder, so that can be, you can download in the Xilinx pattern, whatever the hardware available. So from that you can also get the result also in the hardware also, but here basically we are seeing in simulation mode, okay. You can check whether it is one by one translating, then mapping, it is coming. It will take some time. So and the most important thing is that you have to write the Verilog code properly. If you are any type of, so before after writing this you have to check the syntax. If any syntax error or whatever, the logically this logic should be proper, otherwise the design will not give the proper outputs, okay. So it is very important. Now actually it is taking so much time. You can stop, or sometimes it is showing some. Okay, you can stop. The power X power analyzer output, you can see that this window will a new window will come. Here you can see that the power consumption information will get it. The logic power is 0, signal power is 0. Basically the leakage power, basically the leakage power it is showing, okay. So total power consumption it is showing 3.422 watt. So basically here abrupt just a that is not accurate power consumption, okay. So because these tools are not so much sophisticated for the power analyzer, so to get exact we have to go for any type of ASIC tools like Cadence and Synopsys, okay. So but these tools are very for beginners and these are very important, okay. And it is for the synthesis purpose, this Xilinx tool and functionality for the synthesis and simulation tools, this Xilinx is a very good one, okay. So that is okay. Thank you.